let me share my screen. Will So today the plan is to talk about differentiability, few ideas, and then again get into a problem sheet. So we'll have discussion on some of the problems. Okay, so I hope my screen is visible, and I think
Yes, it is visible.
yeah, thank you. Uh, Fine. All right. So first question first. So let's ask a question. Uh, Suppose let us take a function f, for time being, let me take r to r, and let us fix up some point, say p in r. Uh, Simple question: when do we say f is differentiable at p? Okay. Now, I hope everybody can answer the question. So somebody can quickly unmute and help me out quickly to move further and tell me. Yeah.
Sir, it is the existence of the limit of the ratio of fx minus f of p by x minus p, taking the limit as x tends to p.
Correct. So I just have to talk about something like this. We all know from where this comes, looking like if I'm interested to get the slope of the tangent to the curve at a specific point. So I'm interested in getting the slope of the tangent at p, comma fp, and that is how this fellow comes up. And so whenever this limit exists, so if this limit exists, then then f is said to be differentiable at p, and then in that case we denote the derivative of the function at p by f dash p, and the answer to the derivative of the function at p is nothing but the answer to this limit. Okay, and then we can write this is equal to this. Fine, good. Quick point we noted is every, I mean, differentiability is going to give me continuity. And we all know the next quick remark we always used to, I mean, we used to ask whenever we say implication, the converse. So, converse, yes, is true or is not true?
Not
Not
true.
necessary.
Yes. So, converse is not true, which everybody knows. And now I'm interested in quick example why converse is not true. You all know. Hmm?
Yes, sir, we can take mod of x, mod
Mod
of
of
sin.
x. That's correct. So if I simply look at f of x equal to mod x, and yes, which point?
At 0.
Correct. So not differentiable at p equal to 0. By the way, it's not so useless. I mean, it's differentiable everywhere else. Okay, so though at only one point, it's not differentiable. Fine. Okay. Everywhere else, what is going to be the derivative? I think everybody can guess. Like if somebody asks me, what is f dash at 3? Sorry. What is the derivative of this function at 3? Then what is the answer?
1.
1. At every place, I mean, every x other than greater than 0, it's going to be f dash is going to be 1. And for each x less than 0, f dash is going to be minus 1 simply. Fine. Okay. Moving quickly ahead. So this is not continuous at one point. Sorry, I mean differentiable at one point, but it's continuous. Okay. If somebody wants to, somebody ask a question that I want a function which is not differentiable exactly at 2 points. Exactly 2 points. You know how to construct it.
Yes, we can add another
Hmm.
say mod of x minus 1, suppose.
Okay, so mod x plus mod x minus 1 will fail to be differentiable at 0 as well as at 1.
1.
Okay, and it's continuous everywhere. So like that, I mean, I can simply answer the question if I'm asked to have finitely many points where function is not differentiable. Of course, I'm not getting into more details, like there can be more questions, like how about, can it happen that it's not differentiable at countably many points, or infinite but countably many? Or I can even ask the last question, that is, can it happen that a function is not differentiable exactly at some uncountably many points? Okay, so those questions I'm keeping aside. Moving quickly ahead. So, I mean, once I have f differentiable, suppose on R or on the whole domain for that matter, then I can always talk about f dash. F dash exists. So f dash is a function now that I get. So we can ask several questions like, is a further f dash is differentiable? Is f dash continuous? First of all, is it necessary that the derivative should always be continuous?
Not necessarily.
Not necessarily. And so I just encourage, somebody can give me one example where f dash is not, f is differentiable on full R, but f dash is not even continuous.
Sir, we can take x into sine 1 by x.
Okay, I write the point. F dash need not be continuous, even continuous. Yeah, and one example is coming up. F of x is equal to x sine 1 by x
Yes, sir. X into sine 1 by x.
for x non-zero, and 0 for x equal to 0. This is fx. If you want, see, I understand that something you have to cook with the help of sine 1 by x, but what exactly it is, that you have to be little careful. I want differentiable, but the derivative is not even continuous. Now, is this differentiable at 0?
No, sir.
Huh.
So we
So
can
what?
take
What do you take?
x square sine 1 by x. Then it
Correct.
will be.
Correct. So if you take x square, then this is differentiable at p equal to 0. But if you compute, if you try to work out f dash x, then what will it be? It will be like at p equal to, I mean, at x equal to 0, it's going to be 0. The derivative you can actually work out and it will be 0. And at any other non-zero number, it is like u into v rule you have to apply. uv dash, uv. But when you apply, there will be some term like uh, what you get. Let's see what you are going to get. Yeah, there will be some term 2x sine 1 by x. Yeah, so I think this is not a good example. Let's see. And I get x square. Yeah, it will be cos 1 by x into the derivative of 1 by x, that is minus 1 by x square, and so x square will get cancelled out and you remain with just cos 1 by x minus cos 1 by x. That will trouble. It won't be continuous at 0. This is continuous at 0, but this won't be. And so yes, this is a correct example of differentiable, but the derivative is not even continuous. Fine. So forget about derivative being differentiable. Need not be even continuous. If it is continuous, then even, I mean, one can say that f dash need not be even. Of course, if it is need not be continuous, I can just say of course it need not be differentiable. So even if it is continuous, even if f dash continuous, it need not be differentiable. Fine, we have several examples. So my point is, one can construct differentiable functions which are differentiable, say n times, but not differentiable n plus 1 times. Sine 1 by x is not the only one who helps. Any other example? Um, any other example of
think
Differentiable,
x
huh?
is cube.
At least for second, huh? Yeah. F of x equal to, yeah, I missed what you said.
X cube.
Okay, x cube. Just x cube, you win. Mm, I think I'm missing out something, or I can't
Oh,
hear
no,
you.
no, no.
Yeah,
It
yeah,
is
okay.
not going to work. Hmm.
Ha ha ha. Fine, fine, fine. Okay, okay. See, it can be continuous, but not differentiable. At least that example, other than sine 1 by x. Mod x, you can take help from. Huh?
What are you want that
Ha, ha.
f
I
dash
want.
continuous, but not
Ha.
necessarily f dash is differentiable. Okay.
Differentiable. Correct, correct, correct.
Okay. Sir, I think it is x into mod x.
X mod x. Fine, very good. We can deal with this. And so it is like x square and minus x square. So the derivative is 2x minus 2x. It's continuous, but not differentiable at 0. Fine. And then like this, I can construct. If I'm talking about fourth order derivative, it's fine. We know how to proceed further. Fine. I'm going quickly ahead to um, the composite, or maybe when we solve examples, we'll learn. So then a quick revision or a quick recall is about mean value theorems. Uh, you can see that there are going to be questions. There are always questions on mean value theorems. So before we get into LMVT mainly, before that, let's look at what is Rolle's theorem. I'm sure everybody knows it, but still I have something to say about it. And that I don't know how many of you. So let's see. What's a Rolle's theorem? I'll quickly revise. If you take a function from AB to R or from R to R with two points A and B such that function is, so first requirement, if say I can say continuous on closed AB. Second requirement, if differentiable on open AB. And what is the third requirement?
F of A is equal to F of B.
Function should take same values on AB. So if I want to draw a picture, what I can draw simply is, so you have say points A, sorry, point A and B here somewhere, and the heights are same. F of A, which is height, is at whichever height, at the same height. F of B is also having the same height. And due to this, so this basically says that intuitively you should be able to draw the graph without lifting your hand. And second, the condition basically says that there should not be any corner points. Like I cannot have the graph something like this kind of a graph. We don't want. So what we can do is we can of course have, in whichever way you want to go to, you can just draw a graph. So let me have a simpler version just for understanding. Okay, so this is our graph. And what the conclusion is, there is always going to be at least one point where the tangent to the curve at that point is parallel to x-axis. That is, slope of the tangent is 0. That means I can say then there exists a point C between A and B. This is that point C that I'm looking for, such that the derivative of the function at that point is 0. In other words, the tangent at that point is parallel to x-axis. This is what Rolle's theorem is. This much everybody knows, I know that. But I have a question then. Any doubt about this? This is okay?
Yes, sir.
Recalling. Huh? Now I have some question. Like I mean, why is it said that it's open AB? Like if I have a function which is differentiable on open AB, can I not in fact look at closed AB, for example? What difference does it make? Does it make any difference if I have the statement which have closed AB differentiability?
Sir, it may
Hmm.
violate one
Hmm.
condition that
Hmm.
here at point C, the derivative of that is f dash of C is 0. That means here we are getting a point of local maxima or either
Hmm.
local minima.
Hmm.
So when C is equal to either A or B,
Hmm.
then the necessary condition will not satisfy.
But the point is, you already have FA equal to FB. Now,
Yes, sir.
if you have say point of maxima or minima at the end point, you mean that's what you want to say?
Yes, sir.
But then FA equal to FB, what will that mean then? How the
Sir,
graph will be then?
so I mean to say that if it is said that f dash of C is equal to 0, that means the function
Uh,
has a slope of its derivative at point C. And
Zero.
if C is either equal to A or either equal to B,
Uh,
then it implies that it will have a point of either local maxima or local minima at A or B. But
huh.
when we see in the when we look in the neighborhood of point A, when
Hmm.
C is A, so it can't be either local maxima or local minima. In that way, we can also see that. The,
Uh, okay. Sorry to interrupt, Sunil, but what I'm asking, is I'm asking in the conditions, not I'm talking about the conclusion. So if I change the condition from open AB to closed AB, instead of this, if we say f should be differentiable on closed AB, okay, I can have the same conclusion, by the way. Only thing is, what difference does it make? Uh, so the question is, we are putting more condition by making it closed AB instead of keeping it as open AB. If we make closed AB, that means we are putting two more conditions. One is f is differentiable on at A, and it should be differentiable at B as well. These two extra conditions we are imposing. Of course, the conclusion, because I am putting extra condition, conclusion will not change. That conclusion I can definitely say, because if something is differentiable on closed AB, it is certainly differentiable on open AB as well. So you are going to have this conclusion. My point is, have we missed out something? Like, then will Rolle's theorem not be applicable to some functions? So let me be more precise. The question is, does there exist? Does there exist a function f from closed AB to R such that f differentiable on open AB, continuous on closed AB, but not differentiable on closed AB? Then only this will make some sense, that instead of writing closed AB, we are writing open AB. Because there are some functions which, if we write closed AB, are going to be thrown out from applying Rolle's theorem. So our theorem takes care of more functions by writing open AB instead of close. But to say this, we need to have some function like this. Are people with me? Miss, could you get the question?
Yes,
Sir,
sir.
I don't get the point. What is the question? Does there exist a function closed every 2 hours such that it
Hmm.
is defensible in open
Hmm.
and continuous at F, but not defensible on you mean endpoint are not included in the defensible
Yes. Yes.
and
Means at endpoints it won't be differentiable, but except endpoints everywhere it is differentiable. And
yes.
continuity is there even at endpoints.
I think I'm thinking of example.
Ah,
I think in that case of example also roles hold because roles theorem in
correct.
considering defensibility in open.
Correct. That's what I want to observe. That I mean, such functions will not be taken care if we take closed. But I mean, if there is no such function, then it is as good as taking closed. So to
Yes,
convince
yes.
ourselves,
I am getting your point because
uh,
existence of that function will guarantee that you I have to take the open one
right,
rather than
correct,
taking closed. I'm
correct,
thinking on.
good, good. So should I draw a picture? Then you can guess the function.
Yes.
Uh, and I am sure all of us have worked with this in 11th 12th. We have calculated its derivative, but we never bothered to ask a question that this derivative, where does it exist? That we missed to ask in those days. So let's now ask. So let me show you.
Yes.
Uh,
I
now,
think
haha,
10 inverse or 10.
okay. No.
I think no, because in near pi by 2, 10 is
Uh, Tan inverse
continuous.
has no issue. See, let's understand. I don't want differentiability at endpoints. That means the slope of the tangent either should not, there should be kind more than one option for to declare as tangent, like what happens to mod, or the tangent should be perpendicular line. I mean, a line which is parallel to y-axis. Such a tangent line appears.
Sir,
Then,
it is root x.
huh?
Root x.
Root x, fine. You can say root x at 0.
Yeah, yeah. I am considering close 0, 1.
Yes. So at 0, it has got a problem, but at 1, it has no issue.
Yeah. Because I am taking the
Hmm.
one endpoint. If
Correct.
if I get, then I think another endpoint at a
Yes, yes.
simultaneously 2 point. I am not
Good, good. Idea
think.
is good. That's the idea. So I'll draw a picture. I'll just draw a picture. You are correct. That is what we should be doing. Something like this, if I look at what is the tangent at this point. Of course, my
Yes.
drawing is not that nice, but
It is the upper half of circle. Okay.
yes. So if I
I
take
yeah.
-1 and 1,
Root over of 1 minus x square.
correct. So if I take root of 1 minus x square, What is the derivative? Now let's me use the old 12 standard kind of notations usually people use. Then they write dy by dx equal to, and what do we write? We simply write by using chain rule and all. This is 1 by 2 into square root 1 minus x square into derivative of um, 1 minus x square, that is minus 2x. This 2 got cancelled, and I am left with this expression minus x upon square root 1 minus x square. But now, if you ask a question, where does it exist? At 1 and at minus 1, it doesn't exist, in fact, right? And so, but inside, between minus 1 and 1, this expression is very much available. It's so
Yes,
function
it's
is
very important.
differentiable. So it's differentiable. This is exactly the example that we are looking for.
And roles is always hold because in the point itself,
Uh,
the 0 point, yes, they
yes,
are
correct,
parallel to it.
correct, correct. So that's the point I want to just highlight. Usually we, so means the theorem is, when do you say something is a theorem? So a theorem basically is something which is, you collect all several examples together and declare it as a property that they possess. There is a common property that all those examples possess. That forms a theorem. So what we try to do is, for developing a final version of the theorem, we try to cover as much optimum possible uh, categories of functions. So this is the optimal now. When you say open AB is something minimum that is required. If you reduce it further, I mean, you cannot uh, come to the conclusion. You won't get the
Mm.
conclusion.
Yes,
That
yes.
is the thing. That is the thing. In fact. Okay. Good. Is everyone okay with this? What I have discussed. I'll just move further. Shall we go ahead?
Yes, yes, sir.
Yeah, yeah. Thanks. Now, LMBT, I'm sure everybody is comfortable with the diagram and all. Everyone knows. So if you have point A and B here, and now you don't have the restriction of equal height, so you may have the curve going in different way. So what you do, you simply join these endpoints by a straight line. This point is AFA, and the other point is BFB. Then you always find a point on the curve between A to B such that the tangent is parallel to this line. This point has got the tangent parallel to this line. How do you write this? You write it as f dash c, that is, slopes are equal. So slope of the tangent to the curve at this point, that is f dash c, is equal to slope of this line. And slope of this line is fb minus fa upon b minus a. So that's what LMVT says. So that whenever you have a function differentiable on open AB and continuous on closed AB, you always have a point, at least one point. There are many, I mean, more than one, two, there can be, such that this happens. Fine. Okay. Uh, are you done with Taylor's theorem and the problems based on Taylor's? I think in the
Sir,
August.
in Taylor's it is one time.
Correct.
One time discussed in our class of very
Ah,
few at the beginning of first of the class of this session,
correct.
but
Correct.
we are not I think so much problem done with this Taylor's theorem because we are all of aware of that what it is, but it is
Okay. Okay.
analytical thing about this and those
Ha ha ha.
remaining term or reminder form
Ha
this
ha
much
ha.
not done in
Okay.
our courses.
Okay. Okay. Let's see. Let's see. So, quick point I just want to mention here is, uh, like, you know, if I take interval a to x, okay, what do I get? Actually, is something like there exists some f dash c such that fx minus fa, I can write it as f dash c times x minus a, right? I'm replacing b by x, that's it. And so I get f of x is equal to f of a plus some f dash at c, f dash at some c times x minus a. So this is like the first version, I can say, a small version of Taylor's result
Yes, sir.
that, I mean, you can try to approximate the function, or rather develop f of x, value of fx, at least in some neighborhood of a, in this way, right? This is the first version, we can say, which is actually LMVT. Then yes, if you want more derivatives to get involved, you what you get is the Taylor's theorem, ideally. And so of course, if I want to write equality, then this has to be some point between a and x. But with maturity, one can say f of x can be retrieved using the values f of a, f dash a, f double dash a. If these values are known to me, then we can try to retrieve f of x at least in the neighborhood of a by this expression, something like x minus a by 1 factorial. That's what we got. Then x minus a square by 2 factorial, and so on. Now, if you want equality, either you have to say kind of dot dot dot, but then that is infinite series. So there is a question of convergence. Or if you want to stop at some point, you have to then look at the special term which we call it as remainder term, Rn, and that will again consist of some point between a and x, the derivative, nth order derivative or whatever that comes into the discussion, but it will have the derivative at some point in between. But practically what people do is they are okay with writing this approximately equal to, and even working with the derivative at a itself. All right, and then x minus a raised to n upon n factorial, or n plus 1 upon n plus 1 factorial, whatever the notations are. But now this is enough, and practically people use this only for, you know, retrieving function values at the points which are very close, near to a at least. So knowing only these values, we can obtain the value of the function at any other point near a. That's the I can say consequence or main use of Taylor's theorem. Fine. So why I mentioned it, because LMVT becomes like kind of first mm, understanding or first version of Taylor's theorem, a smaller version, which involves only first order derivative. Okay. One more question somebody has asked, which I'll quickly get into, that is L'Hopital.
Yes,
So
yes. There are.
some people write HOS, or some books they don't write HOSPI. So it is pronounced as L'Hopital rule. Now, see, as a simple version, I see I cannot give you all the ideas, but still I can just show you one. Let's see whether this is, yeah, this is one version which is simplest that I can take. It is from Kumresan sir's book. Uh, what does it say is simply is, you can just look at it. It's, by the way, it's application of CMVT. The proof involves Cauchy's mean value theorem, and it's easy to guess why, because f dash x actually is fx minus fa upon x minus a. Those things gets involved. So you have Cauchy's theorem, mean value theorem. Fine. You see this. The point is, you take an interval, and a can be either, I mean, one of the end point. So it can even be plus minus infinity 2, and look at two functions defined on other than a. I don't need them to be available even at a, differentiable at a. Other than a, they are differentiable. And the denominator, we want to talk, basically we want to talk about limit x tends to a of fx upon gx. This limit we want to compute. This is the question. We want to compute this. So if we observe that these two limits, that is limit of numerator x goes to a and limit of denominator x goes to a gx, if these two limits are equal, okay, that is a, they are denoting it by a, and not just equal, if they both turns out to be either 0 or infinity, okay, where a is either 0 or infinity. Now look at this limit, another limit, limit x goes to a of f dash x upon g dash x. We denote it by b. Now, if we know that this b exists in R, exists in R, okay, or b is plus minus infinity, so even it can be plus minus infinity. It has a meaning. I hope you know what you mean by limit is infinity. It doesn't mean it doesn't exist. It is infinity. So the answer, the expression tends to infinity. By the way, this is g dash. In that case, this limit and this limit are equal. So to compute limit fx by gx, you just have to compute limit f dash x by g dash x, and then whatever is the answer you get for this, it will be same for this as well. So practically while solving the problem, you just have to see whether the numerator limit and denominator limit separately, is it both 0 or both infinity. In either of the cases, what you can then try out is take derivative of numerator, derivative of denominator, and see the ratio limit. What happens to the limit of f dash by g dash. Okay, but of course there are more finer um, points to talk about, and for that, so this is by this book. I can just tell you, basic course, basic course. Do you know Kumresan sir's book in real analysis?
Yeah, yes, sir. We have.
A foundation course in mathematics, that one.
No, not foundation course in mathematics. That
It
is
is real
also a
analysis.
book. I am talking about different basic course in real analysis. This is by Ajit Kumar and Kumresan only. The one you said involves Baba as well, Professor Baba, but this is Ajit Kumar and Kumresan. This is one book I must mention, and the other one, which you all should look at, is the this one, Gorupade and Limay. Do you see this? Can you see my? Yeah,
It's not
this.
visible property.
I'll write the name. The name is A Course in Calculus and Real Analysis. It has actually, there are two books by the same authors. Another one is Advanced Real Analysis. So this is basic. And the authors are Ghorpade and Limay. Very famous, and I don't know. Have you seen? Have you come across this book?
No, sir, I am not coming across this second book.
No.
I have aware of that author because it library there are some book of this author in
Mm-hmm.
library available, but particularly I have
Mm-hmm.
not seen or come across this second.
Mm-hmm. Yeah, yeah. This has got a very detailed, different versions of L'Hopital, and you can carefully go through easy ideas, but they have covered all possible ways
Oh,
to talk about
okay, sir.
L'Hopital rule. So do refer this, and if you are not getting, you can just ask me. We'll see how to get it. Hmm?
Okay. Okay.
Okay, so this is, I think, enough. Now we'll move to problem sheet. So let me quickly share the um, link so that you all can access it. Okay. Yeah, I've posted the link in the chat box. You all can please open and see whether you get the same questions, because which I'm showing you. Could you open it and
Yeah, yeah, sir. It is open.
means questions are matching? Means I don't.
Yes,
I've
sir.
checked once, but will be still okay. Yeah. So let's take your time. 2 minutes. Go through. Okay. So uh, which one you can quickly handle? So those we will not discuss. First is okay.
Yes, sir.
Just plot the graph and you will know that it's not differentiable at so now mod x minus 1, how does it go? So actually mod x is this, minus 1 will take you down. This is mod x minus 1, but this is the graph for mod x greater than 1, so after 1 and before minus 1, that is the graph. And in between it is just 0. So this portion will not be there in the graph. So finally, what is the graph? It is simply this, then this, and then this. This
So
is
it
fine.
is
And so,
not
correct,
differentiable is -1 and 1.
correct, correct. It's differentiable at 0, but not at minus 1, 1. Fine. This you can check out for real. I mean, how to go for it. Let's not solve. Just give me the idea. How will you go for it?
At first, we need to take check it is whether it is continuous or not before going to differentiability. And if it is continuous,
Hmm.
then we can get a condition on A on the unknown A and B, a relation between A and
Correct,
B. And
correct.
after that, if checking differentiability, then we will come across some other condition of A and B. That is
Right.
why there are two equation, relation and two unknown. We'll
Yes.
find out
Done.
the value.
Very good. So let us not do that. Even for this, we know what is. going to happen because h of 0, h dash 0 is known to us. So f dash 0 is simply applying definition. So f dash 0 is limit x tends to 0, fx minus f0, but f0 is 0 upon x minus 0, that is x, right? And so when I say uh, f of x, so what do I get is limit x goes to 0, x cos 1 by x uh, upon x. Right. And now, what to do? How to handle this? Yeah, it's not very straightforward, but hmm, this is fine, no?
Yes, sir.
So
Sir, are
this,
you taking this question number three, I think?
yeah, question number
Yes,
three. Yeah, yeah.
yes, yes, yes. And we are given that h of 0 and h dash 0. Okay.
Yes.
Sir, existence of h dash 0, uh,
Hmm.
it is, uh, it should be limit should exist. Okay.
Correct.
And this something, I think it is hx should be at least a, degree of hx is greater than 1, I think.
See, I don't know whether hx is a polynomial.
Uh,
It is just
uh,
one. It can be
yes,
any function.
yes, I am saying that whether it is x to the power 3 by 2 or something like that, it is not, I mean, not going to the polynomial, but degree of
Huh.
some, uh,
Yeah, it might be. It might be.
otherwise the limits would not exist because it is less than x, some here cos 1 by x causing problem, and
Hmm.
in below that is causing problem.
Hmm. Hmm. Right. But how do we make use of this information now to talk about f dash zero?
Yes,
We can first
I'm thinking.
use L hospital
Huh.
rule, then put x equal to 0.
Okay. So, fine. So, L'Hopital, then you need u into v to go about it, right? You can do that.
But
Sir,
here using L'Hopital cos 1 by x, it does not exist. Okay. Limit
Hmm.
derivative in 0.
Hmm. Hmm. Right. That is again
There
a
are the
problem.
condition of L'Hopital also
Like if I
satisfied.
want a form f by g, how do I convert this into the form f by g? That is again a problem.
sir,
You mean here, L'Hopital?
sir, if we take h of x as
Hmm.
x
Hmm.
raised, that is x raised to the power something which is greater than 2, then it will satisfy all the condition.
Yeah, but point is the question is a general question. No, means you can't take hx as something. You have this information, and this information is more than enough to talk about f dash zero. Understand? If you take something hx, then okay. For that,
Yes, if there
the
are options, some option, then we can use this eliminate. But here it is not given option. And
Hmm.
hx is in general true for all kind
Hmm.
of function.
I got the point. What I think Sunil was saying. What he is saying is if f dash zero is going to be a particular number, then it is independent of what choice we take for h. Is what you mean, Sunil?
Yes, sir. Sir, actually,
Uh,
if we take h raised to the power something which is greater than 2, then h of 0 is 0, h dash of 0 is 0, and so
correct.
f dash of 0 will exist.
Yes, and it will be
0.
uh,
Or,
right. Your.
yes, sir.
I mean, this is a smart move. Is this clear? What he is trying to say? Because f dash zero is a constant number, actually it is independent of what h you go for. Only thing is conditions should be satisfied. Such choice of h you take and actually compute f dash zero. you are going to get the same answer what we get in general. Fine. So this is a correct move, but I want a more, I can say, more elaborative. Or if somebody asks me now why or proof, then our, I mean, technique fails. So if I want to prove, it's easy, because see, you see, this can be written as limit x goes to 0. I just quickly do that, hx upon x, because such idea is used at different places, into cos 1 by x. Now I call it as some function, say
gx.
gx, and I can call it as so some other function, say tx something. Then this is gx into tx. Now you note that the limit of tx, sorry, you note that this tx is a bounded
Yes,
function,
and
and limit gx is going to go to 0. Why?
for existence of this f dash 0.
Limit hx upon x will go to 0. It will be 0 as x tends to 0, because this is precisely h dash 0. H dash 0, the limit is hx minus h0 upon x minus 0, but h0 is 0. So this is hx upon x, which is 0. That means this limit is 0. The other one is a constant function. So the product has to go to 0. So this is 0. Understood? This is a famous result. So
Hmm.
even if the other limit doesn't exist, if it is bounded function and the other fellow is going to 0, then the product goes to 0. Fine, fine. So I hope it's done. Fourth, I'm not discussing. Enough time we had given. Fifth, what I do is, fifth requires some time. So I want you to do it at home, but I want you to try. We will discuss it in next lecture.
So
Yes, yes,
what is the
sir. And keep the try, written try intact. Don't
Yeah, yeah.
forget.
Yes,
Okay.
yes,
Yeah.
yes. Yes, somebody was saying something.
so what is the final answer of three? Question
Of
number three.
3, 0, 0. The answer is 0. Here it is.
Okay, sir.
Yeah, yeah. Now, sixth, 2 is interesting. Look at it first. Take your time. I'll take it on the other page. My screen may not be visible clearly. Mm. Yeah, any idea? See, there are different ways to manage this, but I would, I'll write just one line. So we want solution of this. That is, we want values where this curve intersects this line.
Sir, I think that two
Ah,
solution is possible because
okay, okay. That is the catch actually. So, can I can I plot pi cos x for few known values at least?
yes, sir. If we are know cos, what is the sketch of cos and pi?
Uh,
Just is scale it up
Correct.
by pi unit.
So correct. So this will be pi.
Yeah,
So cos means at zero. At zero,
it is pi.
the value is pi. All right. Now it will start coming down, and if we are drawing here pi by 2,
Then it is 0.
it is going to be 0. So it will simply come down, and it will become 0. Then at pi, so at pi by 2, this is 0. This value only I am writing. Now at pi, it is going to be minus pi, because at pi cos pi is minus 1. So at pi, the value is minus pi. Now at all these points, at 0, this is 0. At pi by 2, fine, this is minus pi by 2. I mean, I'm not converging over, it's not a notation. I'm writing minus x values down. So at pi, it is actually minus pi. So you can see that at pi, in fact, the curves should match.
Yeah.
Okay. So I'm just drawing a curve, and later it should come up, by the way. Like at 3 pi by 2, again, it should become 0. So I'll draw a point over here, and I have a curve going like this and going up again. I think I have a better drawing. Okay, kind of this, and then again it will go up. Fine, and same picture will come on the other side. We'll have, I don't care what happens, because see, this is the line I want to now look at. Now, if I want to draw this line, let me draw it more precisely. So, by the way, it has to cut here. Okay, it has to cut at pi, because we know at pi both are equal. And so if I, and then it has to pass through this, the line should pass through this point as well. So such a line I want to draw. So when I draw that line, you see what is happening? Huh?
It is intersecting at 3 points.
At 3 points. That is something very interesting thing that happens, and that is going to happen because this curve comes down and goes up. And so if you are, and exactly at minus pi, it has the infimum. Now if you want the line to pass through this point, it has to cut the curve before. It cannot be tangent
Right,
at the
sir.
infimum, because if it is at tangent at the infimum, it has to, the slope is 0. Understand? So this line can never be a tangent. that forces us to cut the curve somewhere in between also, and so this is the correct answer. I'm sorry, I have to.
Sir, I'm
uh,
not getting the logic by say, this why it is cut tangent cut and why it should not be a tangent. This
I'll
logic,
tell you.
that
Yeah,
is
yeah,
too obvious.
yeah, I'll tell you why. Because at pi, it has pi cos x has got a minimum at pi.
Yeah,
So if it has got an infimum, the we know that whenever function has local maxima or local minima, the derivative has to be zero.
yes, yes,
So the if at all it is a tangent, then the slope is zero. Means it has to be parallel to x-axis. So this line definitely cannot be a tangent.
yes. I'm getting the point. That is
Correct.
why it have to
It
cut.
has to cut then, right? Good.
So without sketching the graph, is there a different approach?
That's tricky. That even I have not completed the final argument, so I felt that this becomes a much, I mean, uh,
It
better
all if we
approach to get into. Huh.
yes, because if we try to without a graph, then it is a transcendental involvement. I think quite bit long.
Means it is lengthy.
Sir,
Sir,
it
I
is the
know.
question asked in previous 2024 in statistic paper
I
also.
think, yeah. This is,
In
I have
statistic
picked up
paper,
the question from some
yeah.
question paper, right?
And this
Yeah.
and most of the cases, most of the student done at option two, B here two.
That is,
That
that was wrong.
yes.
Right. Yeah, somebody was saying, Sunil was saying something or something, someone else.
Yeah, yes, sir. Sir,
Yeah.
sir, there are some functions in
Mm,
which to
mm.
sketch the graph is getting more difficult.
Right.
So
So
in
see,
that case,
my point is, they when they frame the question, no, I mean that is what my understanding is about this question. In this question, what they are trying to test is basically the graph, uh, skill of looking at the graph and looking at infimum. So one should be able to understand that if you are trying to draw a line which is cutting the curve at infimum, then that line cannot be tangent line. That one has to, means that's what I guess they're trying to check by this question. So sketching skills only are trying to check actually. Okay. So otherwise, if the expressions are complicated, certainly there it cannot be solved by graphical technique. You need some other way out. That is in fact a hint if the expressions are complicated. Huh? Yeah. What else? Hmm. What about eighth question? Can we look at eighth quickly? Is it okay if I extend by 5 minutes or
Yes, sir. Okay, no problem.
no? I mean, I am asking the organizers
Sir is
also.
asking to organizer.
Yeah, if they are also okay. Yeah, I know you wouldn't mind, but 5 more minutes, please. Yeah, I think we can. If they stop me, we'll stop. Fine. So let's move to the eighth one. What do you think? Can you manage it?
8-1.
Huh?
Yeah. I will manage.
Okay, fine. So basically, what you try is derivative of f dash. So I have one bar coming up of zoom. Huh. So f inverse, the derivative of composite and derivative of f inverse. So try to, I mean, work out. So maybe we can, this also we can discuss in the next session if you want. But in between, if somebody has got the answer, I'll be more happy. So, getting to the next page.
Sir, if F
Yeah,
inverse exists and F inverse is also 1 to 1, then it will come such that F inverse derivative of F inverse is the reciprocal of F
F dash.
F dash. Yeah.
Correct, 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 correct. You are correct. That needs to be used here. So you need some idea of inverse image and so on. So see, sit and work out. I think you all will be able to do it. Uh, so let us look at. Oh, 9th is okay. Have you seen such a question? 9th. It is again a famous situation. So,
Yes, we are saying 9.
uh,
It seems like Lipschitz continuous type.
yeah, kind of, but it is something more than that actually. If you see the condition, the power is 3 by 2 mod. It's not just mod x minus y, so it is a little more than what Lipschitz asked for. So what will happen actually is very interesting thing happens. This power makes a difference. So uh, what a hint
Sir, I
is
think
ah,
I think
ah,
here mod of x minus y raised to the power 3 by 2.
hmm,
Uh, in mod function, we can break it as mod of x minus 1 and mod of x minus y raised to the power half.
very good,
And mod of and rearranging this mod of x minus y under the f of x minus f of y because
very
and
good.
considering x not equal to y.
Hmm, right. Yes.
Yes. And after that, if we apply x approach to y, that
Correct.
means
Correct. Correct. Very good. So f dash y actually becomes 0 for all y.
yes,
That means f dash is 0. So in fact your function f is constant. Understand? So in fact it's a general scenario that if you take mod x minus y raised to alpha for any alpha greater than 1, if the inequality is satisfied, then f becomes constant. So that's why when they are giving f of 2 equal to 2, in fact fx is 2 for all x. And then this is okay. I mean remaining can be easily handled. Okay, so the observation is if you have a power greater than 1, then function is constant. Fine. Uh,
yes, sir.
this this is a very interesting question, 10th question. But with that, I am going to discuss in the next lecture. This is based on mean value theorem. That's a hint.
Yes, sir.
So you see
And keep
how.
the term as intact MBT because we can easily
Uh,
recognize.
yes, yes, no problem. Okay. So I think we need to wind up. Um, let's wind up. This is L'Hopital. You can see that. Okay. So I hope I'm okay with this. I still have some more questions based on definition two, definition itself, that we will discuss in the next part.
Yes,
All
sir.
right.
Sir, I think
Uh,
I request we are
yeah.
requesting for accountability and uncountability because there are
Ha.
something question.
Yeah. Yeah.
You would need not
Ha.
formally teach us, but you
Ha.
I think if you share some question which can trigger our confusion also, then it
Ha.
will
Yeah,
okay.
actually, I
If
tried searching for the questions in Jam
yes,
test, but I couldn't find. Like, if you can quote something, I will get the idea exactly what you want. Then I will.
okay.
Even now, you can tell me. I'll write it down.
Yes, sir. Because in some problem you got continuity or defensibility,
Hmm.
uh, sometime we need to use the accountability idea for such cases also. Though they
Okay,
are
okay,
not,
okay.
uh,
Okay, okay, okay.
they
Okay,
are used
I'll
in the
see.
in
Huh.
between problem solving the problem. It is not formally mentioned in the syllabus also, but it is used
Okay. Um.
in the integral also, indefinite integral of Riemann integration.
If a function is not continuous at
Yeah.
countably many points, still and continuous everywhere else, then it
Hmm.
is Riemann integrable, something like that. You mean?
Hmm. Yes.
Okay. What we do is, so in the next session, you come with some concrete problem, like one or two problem, or you are
Okay.
asking me to give you the question. If you had come across any one problem at least, just
Yes.
tell me, because I'm still not able to means make out what exactly you are asking.
Okay. Okay, sir.
So maybe one sample question, if you bring on the spot, we can discuss
Yes.
something.
Yes.
No
Okay.
problem.
Okay, sir. Okay. Okay.
Yeah, yeah, fine, fine. So I'll stop sharing.
Participants, any queries you'll have? Any more queries? Okay. Thank you so much, sir,
Yeah, yeah, yes, my pleasure,
for
Tina.
the section. And thank you, participants.
Yeah, yeah.
Thank you, ma'am, for organizing this beautiful session.
Welcome. Welcome.